Okay, let's look at one other example. This is the America Test Kitchen cookbook. And if we flip this open, here are thin and crispy chocolate chip cookies. Okay, this would be kind of fun for me to bake a bunch of cookies and bring them to class. And we could have cookies, but you can enjoy them, I guess, just visually. So here what we have is a recipe. I think a recipe is another good example of structuralism. You can see here, this is divided into several things. I always like America Test Kitchen because they experiment with all of their cooking, and what their goal is what is the perfect recipe. So here's an entire book of like perfect cookies, and I also love their book on perfect cake and their book on perfect bread, and so it's nice what they do, and they do this section here where they'll tell you, why does this recipe work? You know, so you learn a lot about cooking from reading this and seeing what they did when they tested and when they experimented with things. Now, when we look at a recipe, this tells you things like, this will make 40 cookies. All right, that's great. It also tells you, here's everything you need in order to make those cookies. So these are all the ingredients, and you have to make sure you have these things and this amount of these things. And then the most important part of the recipe here, and let me bring this a little closer, where we can say, okay, these are the steps. And you can see that first I have to adjust the oven rack to the middle position. So they don't want me to cook the cookies on the bottom position of the oven rack because that'll cook the bottoms too much. They need this in the middle of the oven. It's on baking sheets with parchment paper, and then the first thing I do is whisk flour, baking soda, and salt, those dry ingredients. They get mixed together. And the next thing that I do is mix together melted butter, granulated sugar, brown sugar, and corn syrup. Now, all on low speed, mix them thoroughly for about a minute. Then I add egg yolk, milk, vanilla. And you can see that this gives me all the information I need, and I need to do one step at a time, following it. That's structuralism, that this, like that Rubik's Cube, this is the formula. But I don't want to start with number 4, you know, and I don't want to mix up which direction I go. I want to do this in order if I want chocolate chip cookies to be made from this recipe. So here are the chocolate chip cookies I made yesterday from this recipe, and yeah, they're good. Now you can ask, did I follow the recipe perfectly? And you know what, I made a mistake with the recipe, but the cookies turned out fine, because what I did was, where it asked for light brown sugar, I actually put dark brown sugar. So you can kind of see when you look at my cookies compared to the cookies here, that mine are a little bit darker. Why? Because brown sugar has molasses in it. And so light brown sugar has half the amount of molasses, whereas dark brown sugar has more molasses. So these cookies taste great, but they taste with a little bit more of a molasses taste than they do than if I had put less of the molasses and used light brown rather than dark brown sugar. So again, that's maybe a place where I tampered with the recipe by mistake, but I can also then decide, you know what, maybe I like that better. So maybe I want to keep my recipe the next time I do it this way, because I know that it worked and the cookies were great. Okay, so chocolate chip cookies, another example of structuralism. Okay, here's one more example of structuralism, and we might do this a little later in the lectures, just because it's kind of fun. And sometimes if you like puzzles and you like figuring things out, sometimes that's a structuralist part of your brain that likes to figure out, like, what's the formula, what's the key, what's the code, and what is this about, so that I can figure out the meaning of something that looks so complicated. So this is a game called Powers of Hanoi. It was actually invented by a mathematician. All right, if I flip this, you can see that I can put these 3 pegs right here. We'll see how well this works today with this game, and actually with this camera angle too. But I think you might be able to see it from above. All right, this has a bunch of different discs, and you can see that the discs are in various sizes, and they go from big to small, and there are 9 of them. So here we have this stack. Now, another thing that you'll notice, I always say, look at the first functional elements. You'll notice the difference in color. The difference in color is actually part of the solution of this game, and the solution of how to do this with the least amount of moves. So if I start with 1 disc, yeah, the goal of the game is to start with a stack here and move the stack from here to here with the least amount of moves. Now, if I have 1, that's easy. I can just pick it up off of this and move it over in 1 move. Yeah, so simple. Now, but if I have 2 discs, and we're using the ones that are a bigger one and a smaller one here. So these 2 together here. Now, the other thing to know is if I move this over to here, 1 move, I can't move a larger disc onto a smaller disc here. That's incorrect. Yeah, so that's not possible. So when I'm here with this, how do I get this stack from here to here with the least amount of moves? Now, when we had 1, we move 1 move. When we have 2 discs, suddenly I have to go 1, 2, 3. It's 3 moves to go from one side to the other. Now, that's great. Let's try it with 3 discs here. All right, and I'm going to show you the solution. The least amount would be to do this. 1, 2, 3, 4, 5, 6, 7. 7 moves to go from one place to the other. Now, let's now do it with the 4th one, and we'll see how many it is. So when I'm here, I now do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 moves to go from one side to the other. Okay, let me give you the solution for this, and then we'll look at the formula of it, of how to do it, because I can do it with 9, and you'll see how exponentially it keeps going up with the number of movements that it can be. And if we had, there's a point where you have 9 creates a bunch of different moves, and I don't know in the top of my head what it is, but I'm gonna here, let me project it. This is how many moves it would take. And here's actually the formula to figure out how many moves it takes. There's a couple different ways that you can figure out how many discs and how many moves it would take to get from one side to the other on these 3 discs. Yeah. Now the solution is simple. It's this. And it has to do with the colors. And you notice that I can never put a bigger one on a smaller one. So always, wherever they are, the smaller discs are on top of the larger discs. So there's multiple ways I have to shuffle them in order for that to happen. But you'll notice that when I was here with 2, on the ends, I always know that the very bottom should be an opposite color as the box. So that you'll notice that when it's solved, each disc has the opposite color, so never in my solution did I have two of the same color touching each other. They were always opposites when they were here. Yeah. So when I moved the 4, I also know that on the ends, I like the opposite color as the box. But when I'm on the middle, this likes the same color in the middle here. So this, when I moved this, you'll notice the solution was to move this to the middle, to move this to the end. I then moved this on top of this, which allowed me to move this color again to a middle. This shouldn't go on this one, so I knew it only could go over here. That would allow this to go here, allow here to go here, which freed up this big one to come up and over to where it needs to be for the solution. Now, that allowed me this color I don't like on the ends, so I put it here. This color could go here. That would allow this to go here, which frees up this one to then go to here. This one moved to the middle because it's the same color, opposite color there. So again, that perfectly made sense. The thing that I really want to show you is the structuralism of it. There's a formula, there's a way of moving it, and then all I have to do is just simply follow it. And each time there was really only one choice that I could make of how it can move where I satisfied the formula. So again, this is a puzzle, puzzles are great because they have solutions, and there typically is one kind of solution, and this is kind of fun. You can let me know and I can bring it. I keep this at the dance office, so someday if you're really interested, you can try and solve it with all the 9 discs now that you know the algorithm and the structuralism around this device.